So I will get started. So for those of you who don't know me, my name is Shelley Shepherd. I am the Program Manager of New Waterways, which is the, hi Becky, how you going? Which is the capacity building program for water sensitive urban design in Western Australia. So firstly, I would like to acknowledge the Whadjuk people of the Noongar Nation on whose land I am sitting today and our presenters are, and recognise the incredible contribution that the Aboriginal culture makes to water and resources in the environment. It is pretty phenomenal. And also just to recognise that hopefully there's people on different lands apart from ours, so we acknowledge that connection to country. So this is a webinar by or brought to you by New Waterways. As I said, we are the capacity building program for water sensitive urban design, and our main partners are a fabulous group of organisations that are a couple of state governments, so Department of Planning, Lands and Heritage, the Department of Biodiversity, Conservation and Attraction, the Department of Environment, Water and Environmental Regulation, the Urban Development Institute of Australia, West Australian branch, West Australian Local Government Association, and the Urban Development, I said it, UDIA, didn't I? Who did I forget? Water Corporation, terrible. So it's a great bunch of people who get together and identify, I guess, issues that people are finding with the implementation and delivery of water sensitive urban design. This project, you know, we want to try and use water as much as possible. So this project, I think, is awesome. Because if we can utilise grey water from our apartments, from our buildings, to water a green wall that's right outside, isn't that the best way that we can to create green infrastructure? So this is an incredibly interesting and important project and pilot, and we've got some fabulous speakers that are going to talk to you about this project today. I would like to acknowledge the supporters of this project who have been in it for a long time, many years. The Department of Communities, and I have to acknowledge John Savell, who has given the support to this project right from the beginning and fought long and hard to, you know, conquer a few barriers to get it happening, which is amazing. Also the Department of Education, without their support, the trial would not have happened at the Bentley Primary School, and the incredible principal, Steve, out there, who's allowed this project to continue. Bentley Primary School, fabulous little school, awesome. And of course, the Cooperative Research Centre for Water Sensitive Cities as the research partner, and the University of Western Australia. So there's an incredible bunch of people involved in this project. So as I said, we're going to have speakers. We'll have the introduction from Carolyn. We'll hear about water performance from Azrina and temperature from Reza. And then at the end, there'll be a bit of a summary. There's John. Hi, John. How are you going? So John Savell, as you can see on the screen now, the incredible person from the Department of Communities who's been behind this project, major supporter, major funder of it, so acknowledging the incredible contribution of the Department of Communities. So I will just let you know who your presenters are today. So we have Azrina Karima, and she's a PhD candidate in environmental engineering at UWA. She is passionate about water reclamation techniques to provide opportunities for wastewater reuse. Her previous research in Bangladesh was about solar desal and treatment of abattoir wastewater, which now extends to grey water treatment using green walls. Azrina has been investigating the seasonal water requirement and nutrient removal performance of the green walls for almost 3 years. And then we'll hear from Reza. Reza is a PhD student of environmental engineering at UWA. He started his PhD in 2019 with the supervision of Professor Carolyn Oldham and Carlos Ocampo. He is interested in using low-cost and nature-based solutions to solve environmental issues. And Reza's previous research in his master's degree was about wastewater treatment using constructed wetland in Iran. And now Reza is investigating the thermal performance of the green facades at Bentley Primary School. And we'll also hear, of course, from Carolyn Oldham, incredible professor of environmental engineering at UWA. She has and continues to lead a range of research projects under the CRC for water sensitive cities since its beginning in 2013. Carolyn's expertise spans across water flows and nutrient cycling in engineered systems like constructed wetlands and living streams, through to natural systems such as estuaries and coastal wetlands. And Carolyn's led the incredible Green Walls project over the last 3 years and is the primary supervisor for the PhD students that you're going to hear from today. So as I said, please say hi in the chat function, but also that's where you can record some questions. So after the presentations, you will have some opportunities to talk to the presenters and ask some questions. either feel free to put your camera on now, everybody, and say hi. But also, if you want to ask a question, it's lovely if you would do that and turn your camera on at that point, or please just pop it in the chat function so we'll see how we go. All right, so I'm going to hand over now to Professor Carolyn Oldham, who's going to give us the introduction to the project. Thanks, Carolyn. Take it away.
Yeah, I've got it.
Okay. Can you see that? Can you give me the thumbs up if you can see it okay? Great, fantastic. And I'm just going to get those windows out of the way. Good. So thanks very much, Shelley, for that introduction. Bring the microphone a little closer. I'm just going to give a really short background for the project that came into us and what some of the questions were as we started speaking, particularly with John and Shelley, about some of the outstanding questions that I guess practitioners and people who would implement green walls, some of the questions that they still had. And this is what we're talking about here right from the beginning, is green walls irrigated with greywater. And it has some specific challenges. That's interesting. Why won't it? There we are. So, hang on a second. I'm just going to change my. There we are. So green walls in a very generic sense cover all sorts of things. We've got, when we go traveling, we see some amazing green walls, particularly used in urban areas in temperate zones. And there's always a question about how can we implement these in Perth. So first of all, there's just straight green walls because of the aesthetics, the biodiversity that they create. And then, and of course the thermal comfort. And then there's a question of, can we irrigate them with greywater? So the overriding, I guess the outstanding questions that were given to us when we started this project was, how well do green walls survive in a Mediterranean climate, and can we irrigate them with greywater? If we're aiming to implement them here, so irrigating green walls with greywater, what is the appropriate media? What is suitable species of plants? What's a suitable design? Some of the images I just showed you were actually attached to the green wall, to the building wall, and some were not attached, like in the photograph shown here. So what's the best design? What are the irrigation requirements? What are the water requirements of the plants? What's their ability to remove pollutants that might be in the greywater? What are the maintenance costs, and can we reuse the outflow? Is there sufficient volume and water quality to have some beneficial use for the outflows? Or is it better to have no outflows? So there's some questions there. And Azrina and Reza today we don't have a lot of time, so Azrina and Reza will touch on some of these. We don't have time to go over all of these today. In addition to the design and water use of green walls, there's also some key questions around thermal comfort. What is the temperature reduction behind the planters or behind the green walls? Are the green walls providing simply shade that maybe could be provided with the shade cloth? Or is the plant somehow intrinsically important here? What's the benefit of them? What's the effect of green walls in summer versus winter on temperature benefit, on thermal comfort? Is there an impact of planter orientation, meaning east facing, west facing, north, south facing? Do different species have to provide different thermal comfort, and what's the energy savings? So we have here a project that really spans between water and energy, and these green walls have the potential to integrate across both of those. So very short introduction from me, and I'm going to now hand over to Azrina to start talking through the water use of these green walls. And if you give us a moment, I'm going to stop sharing. I'm going to pass my, oh no, we're not doing HDMI. Yep, so you should be able to share now. Yep. And I'll pass the microphone over. And I'll mute, no, I can't mute myself because then that will mute the microphone. So you don't mute, you stay mute on your computer. Yeah. Okay.
Everyone can see that?
Yeah.
Okay. So thank you everyone for joining us here today. So this project has been going on for almost 3 years, and I have been assessing the performance of the green walls in terms of its water use and also the pollutant removal performance. But for today, because it's a very short time, so I'm just going to talk about the water use, the long-term water use, and also the diurnal water use, and how we can take the message to implement that in real life. So as Carolyn mentioned, that the green walls is a generic term for a different sort of living walls or green facades. We see that. So the green walls can be divided in two broad categories. One is the living walls and one is the green facades. So the living walls are the modular vertical systems that are the plants if they're rooted on the wall itself with the help of modular pots or modular panel system. And for our project, because we need to need a subsurface irrigation system because of the greywater, so I think the best one is the green facades. But within the green facades, there are two types of green facades, which is attached green facades and detached green facades. And the difference is that when the plants are rooted on the ground and it attaches itself with the building wall, it's called the attached green facades. And if it use the help of any trellises or other support system, it's called the detached green facades. And our project is about the detached green facade system. So because of the water use, the subsurface irrigation, we choose the detached green facade system. And the green facades or the green walls in general terms, this has been traditionally used for providing the shade and aesthetics and amenity. The functional understanding of this the usage are for its thermal, because of its thermal benefits. And also there are research about the green facades or the green walls to assess the performance as air purifier, its passive acoustic insulation, and also to increase the biodiversity. But there are only a few research going on about its water pollutant removal performance. So the question here is, if we implement the green facade or the green walls, what could be the potential water source? Because for plants to survive the plant, it needs water, and we have reduced a shortage in clean water. So the question is, can we use a different water source, which is the greywater, because it's light wastewater in nature? So the question is, and if we use that as subsurface irrigation, can we use that for green facade irrigation? So only, as I mentioned, only a few research is going on about the green facade, which is irrigated with the greywater. In Monash University in Melbourne, there is a research about the laboratory scale green facade, which showed excellent nutrient performance, nutrient removal performance. It's about 80 to 90% removal of total nitrogen, biochemical oxygen demand, and total suspended solid reduction. But the media in the system was maintained at a water saturated level. And also the Melbourne has a different, which is a temperate climate, so which is different from here in Perth. So the question, we have different knowledge gaps or questions regarding that, which is, if we make this green facade system in a large scale and outside the laboratory, can we maintain the water saturated level? And can the plants survive in Mediterranean climate, which we have a hot, dry summer and a wet winter? So what could be a suitable media for the plants and the suitable plant species for this system if we want to implement that. Also, the seasonal water requirement, how we treat the irrigation, summer versus winter, and how the plant will use the water. Also, if we have outflow generated from the green facade, how are we going to use that, or whether we want to use it or not. And lastly, the pollutant removal performance and the ongoing maintenance cost. We have all of these questions, and I'm still working on to answer all of the questions. But for today, I'm just going to focus on the water performance of the green facade. So as Shelley mentioned, that this is a Bentley Primary School. We have our project going on. The left-hand side, we have the aerial view of the Bentley Primary School, where in the middle, it's showing that the X is locating the gray flow probe, which is the greywater pump, and the toilet and hand basin where the greywater is generated. It's indicated with the black star mark here. And these 5 red bars are showing the green facades. We have 4 green facades with plants and media, and 1 control with only the media, the soil media, but there is no plant to check how the plants are performing. So this design and construction took place from August to November 2018. We are from the left-hand side on the top, the planters were installed with geotextile insulation sheet. We have 3 drainage layers, and where the pictures are showing the installation of this. And then we use gingin loam as the growth media. We have drip lines for subsurface irrigation. We plant and then mulch to reduce the soil evaporation. And this is how it looks after 2 years. This picture was taken in January this year. And these are 2 north-facing green facades among these 4 sets of green facades. So the water use, in terms of the application of the green facade, if we want to do this in real life. So for the water use, I divide this in the water balance equation of the planter, which shows that when we put water as irrigation, we have outflow, and then the remaining water would be called the water storage. The water storage is stored in the soil water, and the plant can then use that as evapotranspiration. So that evaporation from the soil and the transpiration from the plants. And we have measured these. We have been measuring this. The irrigation is with the help of a pressure sensor in the inside the greywater pump. We have outflow, and this was designed by Dr. Carlos Campo, and with the help of a tipping bucket rain gauge, because there are sometimes no outflow, and sometimes there is 500 milliliter outflow per hour. So this huge fluctuating outflow cannot be measured with any commercial device. So that's why we had to go with this hybrid technology. And then the soil water is measured with the soil moisture sensors. So the irrigation, for irrigation, we have tested several different irrigation, depending on the weather and also depending on different type of water source, which is steam water and grey water, and sometimes combination of both. I'm not going to explain detail about this, but we have 4 irrigation regimes. And with these 4 irrigation regimes, the planters responded differently. So this graph is showing that on the top panel is the rainfall. The second panel is showing the inflow data, which is the irrigation regime with different frequency and volume of inflow. The outflow, the focus here is the outflow, how it responded to the different irrigation regimes and whether the plants were doing good. So I'm just going to focus on 2 regimes, which is regime 2 and regime 3. The second regime was in winter and the regime 3 was in summer. So here the top panel is showing the irrigation rate, which is around 4 or 5 liter per hour for almost 7-8 days. And it was irrigating with the grey water. So the 5 days we have the school days, working days. So we have 5 days of irrigation, and then the other days, which are which are on the weekends. So these are the water that is left over from the previous day. So with this irrigation rate, we see outflow. There are pretty much consistent outflow happening every day, and it was during the winter. On the other hand, if we go to the regime 3, which is in the summer in December, if we see that irrigation rate increased because we top up the system with scheme water irrigation, and it was about 10 liters per hour. But in response to that, the outflow, there is almost no outflow. So there are only a few milliliter of outflow happened. And it shows that the difference in the seasonality. So then I calculate the average daily evapotranspiration, and it shows that in cooler months, we have two types of species, which is non-deciduous and deciduous. So it shows that non-deciduous has 3.2 liter water requirement, and which was almost double compared to the deciduous plants. And in warmer months, both the non-deciduous and deciduous become almost similar, which is 7.6 and 7.3 liter. So as soon as the leaf appear in deciduous plants, they start to transpire, use the similar amount of water compared to the non-deciduous plants. So then I wanted to measure the plant-specific water requirement, which is which plant, if we can see which plant use more water. They use, when they use more water, that means that they will transpire more, and this will give a cooling effect. So that was our final thought about it. We want thermal benefit from the plants, from the green facades, and also the plant that use less water. So for that, because the evapotranspiration is hard to measure directly, but we can measure the transpiration from the plant with the help of this portable photosynthesis device, and the evaporation from the soil then can be measured with the help of this water balance equation. So I measured the plant transpiration, which is the plant-specific water use, and this device can measure that with when I put the leaf in this leaf chamber, it measures the transpiration or the water with per unit leaf area. So I measured that several times, and this data is from November 2020. It's showing that the rate of transpiration in the west-facing planters, where we have Hybertia as the climber and Hardenbergia as ground cover. So from this figure, you can see that the blue bars, which is the Hybertia, the water requirement of the Hybertia is almost half of Hardenbergia, which means that the Hardenbergia was transpiring twice as much compared to the Hybertia. And if we look at the other data here, so the gray bars here in the third panel is showing the inflow. We have 3 times inflow on that day, and starting from 5 a.m. in the morning till 9 p.m. at the night, I've measured the water use of the plants. And this figure at the bottom panel, it's showing the outflow. There was still some outflow. It was in November. We have a peak outflow at the end of this tree, the third inflow pump event. And we also measure the solar radiation to check how the plant was responding to the solar radiation, and it was measured with the help of the fire nanometer. So the thing I like to highlight here is that if we look at this data here, we see that the transpiration or the plant water use was increasing, and it increased at midday around 12 p.m. And at the same time, the water storage was reducing, and that was that reduced at the lowest level. So which means that this is actually focusing that in case that the soil evaporation is a lot higher compared to the plant transpiration. So if we look at the magnitude, it was just 1,000 milliliter per hour. And if we look at the water storage, which is the soil, water, and evapotranspiration, which is around 120,000 milliliters per hour. So this focuses that the soil evaporation is way more higher compared to the transpiration. So the plants were using less water, but most of the water that was used in the planter is actually coming from the soil evaporation. So the overall finding was that in winter, we have 5 liter water every day used as irrigation per square meter of the planters area. And in response to that, we have 500 ml water to 4 liter water. But in the summer, even if we increase the rate of to 7 liter, but there is almost no outflow. And the plant-specific water requirements shows that Hybertia scandens, which has a lower transpiration rate compared to the Hardenbergia. And why this is important here, because if we want the cooling effect, if we want more cooling effect, we might use some plant that has higher transpiration rate. So Hardenbergia transpires more compared to Hybertia, and this could give us more cooling effects compared to comparatively. And it also Hybertia, because the Hardenbergia has higher transpiration rate, so because it's transpiring more, it will provide less outflow compared to Hybertia. So that's all from my ending, and now Reza would talk about the thermal performance of the green facade. Thank you. So we just
okay. Hi everyone. In the next 20 minutes, I want to give the presentation about the gap and external wall cooling of green facade, especially at the Bentley Primary School. In the last 200 years, the global population has increased 6 times, while at the same time, the urban population has grown more than 100 times. This rapid, radical transformation of environment from native vegetation to largely built up areas cause serious environmental problems, such as air and water pollution and global warming. Therefore, a green wall could be considered as a good solution which can solve some of these problems. Green walls have both environmental and social benefits, including shading and blockage of solar radiation, evapotranspirative cooling from transpiration from the plants, and energy saving. And also cost and environmental benefits, social and economic aspect, and psychological impacts. The first 3 items have been considered as cooling effect, which are the main focus of this study. Also here, there is a link between my project and Azrina's project, which is about the transpiration and evapotranspiration. So the objective of this study at first is reviewing and analyzing the thermal performance of green facade based on published studies. And then after this analyzing, we can find the knowledge gaps, which are understanding the thermal performance of green facade at Bentley Primary School, and understanding the role of plants on the cooling effect of green facade. Thermal performance of green facades are important in 2 different aspects. The first one is building energy saving, which is related to external wall cooling, and the other one is the gap cooling. For the first one, we need to measure and compare the temperature of external walls of wall with and without facades. So here, delta T for external wall is the temperature difference between these 2 walls. And negative delta T means that external wall temperature with facade is lower than without facade, which is considered as external wall cooling. On the other hand, the positive delta T means that the external wall temperature with facade recorded higher temperature than without facade, which is considered as external wall warming. And for the gap cooling, we need to measure and compare the temperature of the area in front and behind the green layer. So here, delta T gap is the temperature difference between ambient air and gap temperature. And again, delta T negative considered as gap cooling, which means that the gap has lower temperature than ambient air. while positive means that gap recorded temperature more than ambient air and considered as gap warming. After analyzing and reviewing temperature from published data, which were more than 30 papers with about 900 hour temperature data, we understood that green facades and green wall have been used in different countries with a huge range of temperature classification from hot to cold, with a minimum and maximum temperature of -6 and 42 degrees. In this slide, so we have the heat maps of green facade with and without facade, with facade and without facade. The top one is for the green facade. The x-axis here is the time of the day, and y-axis is the location of temperature sensors from ambient air to external wall. By comparing these two graphs, we can easily understand the role of plants in reducing gap and external wall temperature. The gap is always cooler than ambient air up to 2 degrees, and the external wall is up to 4 degrees cooler than external wall without facade. And now going to our project at Bentley Primary School. For this presentation, I've selected the north-facing planter during two different weather conditions. One is cool and the other one is warm period. And on the right, we have the location of temperature sensors that we have in front and behind the green layer, and also wind sensor and pyranometer for the solar radiation. First, I'm going to cover the thermal performance during cool period on 21st of July. Again, this slide showing the heat maps of wall with and without facade. The first one and the y-axis here again is the location of temperature sensors from ambient air to external wall, which also has shown on the right figure. We have different temperature sensors in the gap. We have temperature for the sensor for the temperature of the green layer and external wall. Before going to next slide and answer these questions, how does the thermal performance of green facade change over a Dyno cycle? And how does solar hour and wind exposure impact on the thermal performance of green facade? By comparing these two graphs, we can easily see the temperature difference, especially on the external walls of with and without facade. This slide shows the external wall temperature profile of the same planter at the same day. The black line here is the ambient air temperature. The blue line is external wall with facade, and the dashed line is external wall without facade. I'm going to split the day into different periods and explain what happened on that period. The first period starts at 8 and ends at 11. During that period, the temperature is almost homogeneous across different regions because of shading from the next planter, as it's obvious in this photo. 8:30, still we have shade, 9:30, and we can see that by changing time and solar angle, shades move to the other side. 10:30, and around 11, the shades completely move to the other side. So the next period starts at 11 and ends at 4. During that period, which is highly affected by the solar radiation, the external wall temperature of wall without facade is about 15 degrees warmer than wall with facade, mainly because of the blockage of solar radiation and also evapotranspirative cooling. And by checking the photos, we can see that during that time, the external wall without facade were completely covered with the solar radiation. And then going to the next period, which is on the night time, and during that time, the external wall with facade is about 1 degree warmer than without facade. And the reason is that during day, external wall can absorb and store heat from solar radiation and release this amount of heat during night. Also, green layer can act as insulation layer and thermal buffer, which can trap air inside the gap. So the external wall temperature recorded higher temperature. Now going for the gap temperature. This slide again showing the temperature profile for the gap. The black line is the ambient air, The red line is the gap with facade, and the dotted line is the gap without facade. During nighttime, again, the gap temperature with facade is about 1 degree warmer, same as the previous one because of the warm trap air inside the gap. And before going to the next period, by checking the temperature profile, some increases and decreases in temperature can be seen. The result from wind sensor shows that after each wind exposure, the increase and decrease happened. Also, wind can increase and decrease the cooling and warming effect of the green facade, meaning that during nighttime, wind can disturb the trap air, the warm trap air inside the gap. So the warming effect can decrease. And on the other hand, during daytime, wind can facilitate the evapotranspiration, which cause decreasing the temperature of the gap. The next period, which is affected by the solar radiation, is during the midday. It's from 11 a.m. to 4 p.m. And during that time, the temperature of the gap with facade is about 1 degree cooler than ambient air. Now going to the warm period on 29th of October. Again, we have here the heat maps and heat map of the wall with and without facade, which is again showing the temperature difference between ambient air and the gap and external walls of with and without facade. Here again, we have the temperature profile of the north-facing planter during warm period. And during this period, between 8 to 4 p.m., temperature of external walls and also gaps are about 4 degrees cooler than ambient air and external walls of without facade. And during night, when the temperature is less than 20 and around 15, the temperature of external wall with facade is about 2 degrees warmer than wall without facade, and the gap is about 1 degree warmer than ambient air. From previous slides, we understood that green facade can provide both cooling and warming effect based on the weather conditions. But there is a question here. If we replace the green layer with shade sail, is there any difference between temperature behavior and thermal performance of this kind of facade? In order to answer this question, we need to do a new experiment, which I've done recently. So I put a shade sail close to the planter as shading facade. So we have a green facade, shading facade, and without facade. The shade sail can block 70% of solar radiation, same as the planter that we have on the green facade. Also, if you remember, I explained that two main reasons for cooling effect of green facades are blockage of solar radiation and evapotranspirated cooling. So by replacing green shade sail with, we can understand that how much of the gap cooling, overall gap cooling, is related to the evapotranspirated cooling from the plants and how much related to the shading. Again, we need to define some different terms, and the first one is the evapotranspirated cooling, which is the temperature difference between gap of green and shading facade. And again, a negative delta T considers as evapotranspirated cooling, which means that the gap temperature of green facade recorded lower temperature than shade sail. And for external wall, we have the same procedure here. So the temperature difference between external walls of green and shading facade. Here we have the temperature profile for the gap of shading and green facade. The red line is the gap temperature of green, and the dotted line, the red dotted line, is the gap temperature of with shade sail. During this period, which is affected by solar radiation, the gap temperature of green facade is up to 5 degrees cooler than the gap temperature of without facade, with shade sail, when temperature were always more than 30 degrees. In other words, the mean contribution of evapotranspirated cooling from the plants and shading cooling to the overall gap cooling is about 40 and 60%. And for external wall cooling, for the same planters at the same day, again, the results show that the external wall temperature behind green facade is up to 5 degrees cooler than external wall temperature behind the shade safe. And during nighttime, the external wall temperature behind the green facade is up to 1 degree warmer than external wall temperature with shade safe. As conclusion, in terms of gap cooling, during warm weather, the gap is up to 4 degrees cooler than ambient air, and during cool weather, the gap is up to 2 degrees warmer than ambient air. In terms of energy saving and external wall cooling, during warm weather, the external wall behind the green facade was more than 17 degrees cooler than wall behind the wall without facade. And during cool weather, the external wall behind the facade was up to 2 times warmer than without facade. And for the effect of shade safe, during warm weather, about 40% of the gap cooling from the evapotranspirative cooling, which is from the plant, and 60% are from shading. And the external wall behind the shade safe was significantly warmer than behind the facade. Thank you. Now I'm passing the presentation to Carolyn.
Stop sharing. Okay, so I'm just going to okay. So what I'm going to try to do now is just take a couple of minutes to try and recap the findings that Azrina and Reza have presented today, so that you have them all in one spot. So the trials, the pilot scale trials that we've done at Bentley Primary School have shown that green walls, specifically green facades irrigated with greywater, are viable in Perth. As always, we had some death of the plants. I need to stress that after the initial plantings, where the media had fertilizer in it, we've gone almost 3 years now with no fertilizer addition, and that was because we were assessing the nutrient attenuation performance. We haven't shown that today, but we were doing that, and so we didn't want to complicate that by adding nutrients. So we have seen the, if you like, the rundown of the media and the initial fertilizer over the 3 years. That probably is not, we know that's not optimal for plant growth, and some of the plants did not fare nearly as well as other plants. However, some of the planters have had robust growth. There is no question about that. The selection of plants, there's been some conversation going on the chat screen about whether you actually want outflow or not, whether Department of Health allows outflow or not. We didn't tackle that question specifically, but what we've found clearly is that the selection of plant species will impact whether you have outflow or not, and therefore you should choose your species based on what you want. So you can be, I think the results we've shown is that you can fine-tune your outflows by choosing species that have higher transpiration rates. I wanted to stress here because those species may not necessarily be the water-wise species. And that's something to really think about here. And whether I feel we need to think through the communication of this quite carefully because of the strong messaging out there about water-wise species, which in general have quite low transpiration rates, low water use. But if we're wanting to choose plants that have high water use, because you want them to use all of the greywater because you don't want outflow, and the high water use also has higher transpiration rates, which give you more cooling effects, then you may choose plants that are not the plants that are promoted strongly as water-wise plants. So I think there's a careful communication there. Communication is required there. The maintenance questions, The maintenance has been really quite moderate. The pumps certainly have required the greywater pumps have required membrane changes, filter changes. We've required back flushing, the normal sort of irrigation requirements, checking that the flows are working, and there's basic trimming of the plants. But as I said, the maintenance has been quite minimal. We didn't show the details of this, but when the outflow was available, the nutrient attenuation was very good. Over the first year, we got significant nutrient leaching from the media. We could show that quite clearly, but by the time the outflow, but the outflow itself had much lower concentration. So we could compare the controls with the control planters with the planters that had greenery in them, and we could show quite clearly that the effect of the plants was to have quite good nutrient attenuation. So that was an interesting learning. We also found that green walls significantly decreased air temperatures behind them on hot days, particularly, and moderated temperature on cool days. And we could quantify the effect of shade cloth versus the effect of the plants. And that's something that we don't believe has been shown before. Some of the considerations that someone needs to be thinking about moving forward, and some of these we will touch on as we finish up this work. The work that we have done at Bentley Primary School has all been done at ground level. If green walls were to be deployed on apartment blocks, on verandas, balconies of apartment blocks, we'd want to think through the impact of the higher winds. And Reza is starting to pick that apart in really starting to, even at ground level, we can start to see the effect of wind on the cooling effect, of the cooling impact, or the thermal, what might be thermal comfort. And so we can suggest what might happen if you're deploying the green walls higher and higher, which of course then exposes them to higher winds. Of course, the plant species may also want to be carefully selected for the higher winds. The long-term buildup of salts in the media is not really known. We still have living systems and we haven't done soil cores, but the discharge, when we do have outflow, the analysis of that water doesn't suggest there's a long-term buildup of salts. That might be something to explore. Someone's being, that's no one here, no. Might be something to explore as these planters go towards the end of their life, or even in the control planter. We can probably do a soil test towards the end of this project. I think we've shown that it's very possible to take these systems out of the laboratory and into the real world, and there's a real potential for larger scale trials now. If larger scale trials are done, and particularly in apartment blocks, as you take them higher and therefore more exposed to wind, I would suggest that monitoring of those would still add really valuable information to our understanding of how these systems perform and therefore how to best design them into the future. So I just want to go back. Shelley mentioned this at the beginning, but I also wanted to stress the contributions from many agencies here. First and foremost, not just the funding, but the engagement, the funding from Department of Communities and the strong engagement and support from John Savell specifically. This project would have not got off the ground without John. We've had a very strong steering group, and it's been really fantastic working with that steering group. And we've basically had so many government departments on that steering group. Everyone who was interested in this project has been there, as well as Monash University, particularly the researchers who are leading or have led the laboratory scale trials, and City of Canning and Josh Byrne and Associates. It's been great having Josh involved in the conversation as well. So I really thank all of those people. I know there's a number of people today who are listening to this who have been on that steering group, and I really appreciate their contribution over the 3 years so far. And with that, I'm happy, the team, Azrina, Reza, myself are really happy to answer any questions. So I will stop sharing now. Here we go.
That's awesome, Carolyn. Thank you so much. Thank you, Azrina. Thank you, Reza. They were fabulous presentations.